We're continuing with Chapter 2 in the algebra textbook. Chapter 2 is on functions and relations. In this video, we're going to go through Section 2.7, analyzing graphs of functions and piecewise defined functions. So we're going to talk about symmetry in equations. So any equation, whether it's a function or not, has a graph, and that's the idea of we're looking for symmetry in the graph, which means also you can say the equation has a symmetry about it. But if we focus on functions, then tied in with this idea of symmetry, you can think about an even and an odd function. But we're also going to talk about piecewise functions, and we're not going to spend too much time on that. But personally, when I was going through school, I tended to put piecewise functions on the back burner, kind of ignore it. But there's a way that you can think about piecewise functions that I'll talk about when we get to that section that I think will make the usefulness of these types of functions or the reality of these types of functions in real life become more clear to you. Okay, but first, let's talk about symmetry in equations and graphs. The photos in the figures below each show a type of symmetry. And so if we look here at this photo, the idea is if you're thinking about each point x, y in this picture has like a gray value and a color value. Well, if for any point x, comma, y, if you put a minus sign in front of the y, so that means, as we talked about in the previous section, if you put the minus sign in front of the y, you're reflecting across the x-axis. So we go from xy to x minus y. Then the gray value, so this would be like an equation in three variables. You would have the output is z, and the input is x and y. The output is the gray value, the color value. So for any input x, y, you get a gray value and a color value. If you go to x minus y, so you flip across the x-axis, you get that same gray value and color value for any point in this picture relative to this x-axis here. So that's a symmetry. This has about, you could say like the x-axis. I mean, there's no Cartesian coordinate system here, but this horizontal axis, this picture it has a symmetry about this horizontal axis right here. Okay? Now, this picture has a symmetry about this vertical axis here, because if you go to any point, if they make, they define a 0 point, an x, y 0 point, so like this would be the origin. If you go to any point, whether it be positive x, positive y, positive x, negative y, negative x, negative y, wherever, then if you, at that point, you'll have a gray value, a color value. If you put a minus sign in front of the x, so you go from, well, okay, we'll go over here, x minus y, let's say. We're at positive x minus y. Put a minus sign in front of the x, then you go to minus x minus y. You're going to get that same gray value and color value, right? This has a symmetry about what you could call the y-axis. And so here they would have to define a 0 point somewhere. Yeah, I mean, just any 0 point anywhere. And as long as the axis of symmetry needs to, you can just put arbitrarily anywhere. It has to be at the x-axis and needs to be at the axis of the horizontal axis of symmetry. And same thing here, the y-axis needs to be at the vertical axis of symmetry. But okay, if the y-axis is here, you come to any point x minus y, x, y, minus x minus y. So x minus y. Okay, put a minus sign in front of the y. What are you left with? X, y. You're going to get the same gray value and color value. So you can see the idea of a symmetry about a horizontal and a vertical axis. Here, the example they're showing here is that this flower is symmetric with respect to the origin. And I find this, I don't like the example they use here because, okay, well, first of all, what does it mean that this is symmetric with respect to the origin? What that means is that if you have any point wherever, you could come, okay, so let's use their example, x comma y. If you put a minus sign in front of the x and a minus sign in front of the y, what does that mean? You put a minus sign in front of the x, you come here. Then you put a minus sign in front of the y, you come here. You're going to get the same gray value and color value, okay? But to me, this was confusing because Well, that must mean that it's symmetric with respect to both the x and the y axis. And for this case, that actually is the case. This is symmetric with respect to the x-axis, the y-axis, and the origin. However, being symmetric with respect to the origin does not mean that something is also symmetric with respect to the x and y axis. That's what it seemed like to me. Well, if you're symmetric with respect to the origin, that means you're symmetric with respect to the x and y axis. No, you could be symmetric with respect to the origin, but not symmetric with respect to both the x and the y axis, or either. Like, you could be symmetric with respect to the origin and also not symmetric with respect to the x or y axis. But why is this symmetric with respect to the x axis, the y axis, and the origin? Because if we come here and we go x minus y, we come here, stop. Has the gray value changed in the color value from this point to this point? No. So it's symmetric, and that's the case for any point. So it's symmetric with respect to the x-axis. What about the y-axis? Put a minus sign in front of the x. Come here. Has the color value changed? It would change if we came anywhere like in here, but this point, no. So it's symmetric with respect to the y-axis. Okay. Put a minus x, put minus y. Has the color value changed? No. So it's symmetric with respect to the origin. Now, I need to verify this, but I don't know if it mentions this in this section, but if an equation or picture or whatever, we're going to talk about how all of this applies to equations. Okay, but if an equation is symmetric with respect to the x and the y axis, then it also must be symmetric with respect to the origin. I believe that's the case. I'm going to verify that, but if there's a mathematician, leave a comment, but I'll verify that. However, again, what I'm not saying is that if an equation is symmetric with respect to the origin, that means that it must be symmetric with respect to the x and y axis. I'm not saying that. I'm saying if it is symmetric with respect to both the x and the y axis, then it also must be symmetric with respect to the origin. Why? Because I just showed you. You go from, if it's symmetric with respect to the x-axis, then all of these are equivalent. If it's symmetric with respect to the y-axis, then all of these mirrors are equivalent. Well, then if you go across the x-axis, then go across the y-axis, it's going to be equivalent as well, right? So that should be the case. Okay, so that's the idea of symmetry with respect to the x-axis, the y-axis, and the origin. And those are three distinct ideas: the x-axis, the y-axis, and the origin. How does that idea apply to an equation? And we're just talking about general equations right now. We're not saying anything like, we're not constrained to functions. Just think about any equation. Could be a function, but it doesn't have to be. How does this symmetry apply to an equation? Well, if you take an equation, any equation, and you substitute x for minus x, simplify, and you get the exact same equation that you started with, then that means that that equation, or you can think about the graph, is symmetric with respect to the y-axis. We're talking about an equation in two variables. If you take an equation and you substitute the y, every y value, so yeah, you substitute every single x value for minus x, or you can think about substituting every single y value for minus y if there's multiple y or x values, and then you simplify and you get the exact same equation you started with. That means that equation or graph is symmetrical with respect to the x-axis. Then finally, if you take every single x and y variable and you substitute it for the minus version of that variable, simplify, and you get the exact same equation, that means that the equation is symmetric with respect to the origin. Okay, now let's just talk about 3D for a second. You know, you could go from 2 variables to 3 variables, 4 variables. It gets a little more difficult to think about as you get to more variables, but you can imagine we'd have some, any kind of equation that has x's and y, expressions of x's and y's and z's on both sides. And so you've got a point here on the graph, x, y, z, if this has some graph. If you substitute every single z value for minus z, simplify, and you get the same equation, then that's a symmetry with respect to the the XY plane. You see, you have to kind of, and if you went past 3 variables, you'd have to think about this abstractly, but that's the idea. If you substituted the y value for minus y, simplified and got the same equation, that's a symmetry with respect to the ZX plane. Okay, so they give some examples here. They say let's test for symmetry for this equation. This is a function as well, right? And for this equation, this is not a function. So here's y is equal to absolute value of x. And if what you can see is if you substitute x for minus x, you get the same equation. And what does that mean? That means that if you come to x is equal to 2, you get a y value. If you come to x is equal to minus 2, you get that same y value. So that's that symmetry with respect to the y-axis. But there's no symmetry with respect to the x-axis. And for any function, that's going to be the case, right? Otherwise, it wouldn't be a function. To have a symmetry with respect to the x-axis, the idea is if you come to a y value, you get like x is equal to 2, right? If I come to this y value, I get, then that corresponds to x is equal to 2. If I go to the negative of that y value, I'll also come to the graph at x is equal to 2. That's not a function. There is a function that has a kind of symmetry about the x-axis. That's f of x is equal to 0. So this. But that's kind of a trivial case. Okay? But so they test this. They put minus y is equal to the absolute value of x. That simplifies to y is equal to minus absolute value of x. That's not the same function or the same equation, right? They're testing it. They're substituting x for minus x, substituting y for minus y, then substituting both y and x for the minus version. And for the symmetry about the x-axis or the origin, you don't get the same equation. But symmetry about the y-axis, you get the same equation. Okay, so now x is equal to y squared minus 4, that's this graph. That's not a function. But you can see it's going to have a symmetry about the x-axis. And they do this. We're going to work example problems, but they substitute minus y for y, simplify, and they get the same equation. But there's no symmetry about the y-axis or about the origin. Okay, now you might be wondering, well, okay, but when are we going to get to an example that shows how something could be symmetric with respect to the origin, but not symmetric with respect to the x and y axis at the same time? We'll get to that. Okay, here they give an example. This is like the flower example where this is symmetric with respect to the x-axis, the y-axis, and the origin. So a circle, and yeah, if you substitute just minus x for x and nothing else, same equation. Just minus y for y, same equation. If you do both, same equation. Okay, now, I don't want to confuse you here. They don't give an example. Right now, we haven't specifically talked about the idea of a function. We've just been given just general equations that the y is equal to absolute value of x happen to be a function, but we were just talking about equations. I would have liked if they would have given an equation, a general equation, that was symmetric about the origin, but not symmetric with respect to the x and y axis. They didn't. So let me do that first before we go to the next section. Okay? So all we're doing right now, again, all we're doing at the moment is we've learned about this idea of symmetry, how any equation, function or not, can have symmetry to it. We've talked about 3 types of symmetry, and we've been given equations, example equations, that they don't have to be functions, it doesn't matter, that have a symmetry about the y-axis. We saw one that has a symmetry about the x-axis. We saw one that has a symmetry about both the x-axis, the y-axis, and the origin. Now, let me give you an equation that has a symmetry about just the origin and not the x and y-axis. So y is equal to x cubed. Okay, I think it's something like this. Okay, so let's substitute. To test for symmetry about the origin, we replace y with minus y, and we replace x with minus x. Okay, you get minus y is equal to minus 1 cubed is minus 1, so you get minus x cubed. The ones cancel. Okay, you get the same equation. That's the definition for symmetry about the origin. Okay, great. But if it's symmetric about the origin, it's got to be symmetric with respect to both the x and the y axis as well, right? Let's see. Let's test for symmetry about the y axis. So replace x with minus x. Okay, minus 1 cubed is minus 1. Not the same equation. Let's test for symmetry about the x axis. Replace y with minus y. Not the same equation. Okay? It was the case that, if you come here, that for this circle, you could do all three types of symmetry tests and they all check out. But this, it's just the origin case that checks out. So what's going on? Well, look, if we come to a point here and we check for symmetry about the x-axis, replace y with minus y. Come here. That point's not on the graph. The graph doesn't go through this point. So it's not symmetrical with respect to the x-axis, right? If we come here, go replace y with minus y. We're on the graph. See? You have to reflect twice. If we reflect twice, boom. Now we're on the graph. If we reflect twice here, we're on the graph. You see the difference? Okay, so there you go. We've looked at the idea of symmetry, the three different types of symmetry for just equations in general. Any equation, a function, equation of a circle, any equation, doesn't matter what it is, function or not. Okay, so now what we're going to do is let's focus on functions. Let's say we're just dealing with functions. So what we're going to do is we're going to talk about even and odd functions. And I found it was confusing for me. I would forget that even and odd functions, it's related to symmetry. We're still just talking about symmetry. An even function, we're going to see it's a function that has symmetry. All right. Now, but one thing you've noticed though is that when it comes to functions, they can't have, I mentioned this a few minutes ago, but like to have, if we come here to the circle, yeah, this was symmetric with respect to the x, y axis and the origin, but it was because the main reason was because it wasn't a function, right? If you're constrained to have something that's a function, then the symmetry is going to be limited as well. And again, I touched on that a few minutes ago. So when it comes to symmetry of functions, all you have is two types. You either have an even function or you have an odd function. An even function is going to be symmetric with respect to the y-axis. An odd function is going to be symmetric with respect to the origin. That's the only two possibilities. That's it. That's the only symmetry possibilities when it comes to a function. Either you're going to be symmetric with respect to the y-axis, and then the function's given the name even function, or you're going to be symmetric with respect to the origin. The origin. And then in which case it's called an odd function. There's no possibility of symmetric with respect to the x-axis unless you have the trivial case it talks about here where the function lies solely on the x-axis. So it's like f of x is equal to 0. Then yes, by definition, if you replace f of x with minus f of x, you get f of x is equal to 0 again. But outside of that, there is no, it can be symmetric with respect to the x-axis, the y-axis, and the origin. There's none of that with functions. These are only two possibilities. And so how do you test a function to see if it's even or odd? Well, the only difference is you have this, you'll have this f of x notation instead of the y. But it's the same thing. If you want to test to see if a function is even, what are you going to do? Well, okay, this function here, y is equal to f of x. You could make this f of x is equal to, y is equal to the absolute value of x. You could say that's f of x is equal to the absolute value of x. It's symmetric with respect to the y-axis because you replaced, what you do is you're putting f of minus x and evaluating the function, and you get the same function. F of minus x is equal to f of x is in function notation. That's the idea. For an even function, you're replacing x with minus x, simplifying. For an even equation, in any equation, you're replacing x with minus x, simplifying, and see if you get the same equation. Well, for a function, in function notation, what you're saying is, if I do f of minus x and simplify, do I get the original f of x. In other words, does f of minus x equal f of x? If it does, it's an even function like this. It's symmetric with respect to the y-axis. Okay, now if it's an odd function, then the idea is in function notation, does f of minus x equal to minus f of x? It's this function notation that's kind of confusing. So what are they saying there? What they're saying is if we come back to the general equation, so let's do y is equal to x cubed. Let's ignore the function notation. What they're saying is if you replace x with minus x, what do you get? Y is equal to minus x cubed. But then if you replaced y with minus y, you'd get the same equation back. But the way they're saying it here is this is minus f of x, right? It's kind of confusing the way they write all this. But you see what they're saying? It's all the same thing. This is just they're doing this in function notation. This f of minus x is equal to minus f of x. It's this idea here. Now we replace y with minus y, and we get the same equation back. So it's symmetric with respect to the origin. They're just doing that in function notation. That's it. Okay, so let's look at these functions here. By inspection, are they even or odd? This looks like the square root of x. That's an odd function. It's symmetric with respect to the origin. F of minus x is going to be equal to minus f of x. Here, it looks to be, it's not symmetric with respect to the origin. It's symmetric with respect to the y-axis. It's an even function. Here, well, there's definitely no symmetry because if you go across the x or y-axis or origin, there's no graph. So this function is not even or odd. Okay, this video has gone a little longer than I expected, so we'll do piecewise functions in the next video.